left-hand side, I just want to make sure. On the left-hand side, you have two cations. On the right-hand side, you have one anion. So a cation has a positive charge, and an anion has a negative charge. So now, the one that I just underlined three times in red is a cation, and then that is an anion. The other one is listed, is the element itself. Now, it might not be the naturally occurring element, but it's the element itself. Let's just look at the first one, sodium. If we have sodium in our body, and we do, which one do we have? Na or Na plus? Anyone want to take a guess?
Na plus.
One of those two. Which one? Na plus?
Plus.
So if we have Na in our body, there'll be a very severe chemical reaction, and we probably would die, depending on the amount of it.
Oh my.
I'll show you later on. When I wish I could switch to, one of the things I can't do is switch to a video to show you what will happen, but it would be a minor problem. So Na is deadly. How about chlorine? Cl or Cl minus?
Chlorine?
Chlorine.
Cl minus?
Cl minus is the ion, and it is the thing that we find in our body. If we have Cl, or more effectively here, in reality, whoopsie. Cl2, that's how it occurs in nature for a very short period of time. If we have chlorine or chlorine 2, we would be dead. This is a gas. If this was in this room, very, very quickly, all of us would be dead. Perhaps Rochelle would live a little bit longer because she has a mask on, but not very long, right? Unless we get out of it. So chlorine, sodium, deadly molecules. Anyone know what this is?
Potassium. Oh. Sodium chloride.
Anyone know what sodium chloride is?
Table salt.
Table salt. Okay. That's table salt. That's important to life. But sodium and potassium, sodium and chlorine are deadly in its unreacted form. So there's cations and there are anions, and this is how important it is. So in order to get to that question about cations and anions, let's go back a couple of steps here. So this is called subatomic particles. So there's a subatomic particle with a charge that's positive, a charge that's neutral, and a charge that's negative. The one when we talk about the charges that are negative, we talk about electrons, and we're really, really worried about electrons. That's, in fact, almost all that we're worried about in this class. Electrons are in shells, and those shells get progressively bigger and bigger, and they get further and further away from the center of the atom. And what is the center of the atom called?
The nucleus.
The nucleus. And in the nucleus here we have two subatomic particles, the proton, which is positively charged, and the neutron, which is not charged. Right? So there's protons and neutrons. If we were worried about movement of protons or the movement of neutrons, then we no longer are worried about biology, and we're worried about nuclear bombs. Okay? I'm not worried about nuclear bombs, so I'm not going to worry about movement of protons and neutrons.
So that's what a nuclear bomb is.
Right. So there are these things called hydrogen bombs. There's neutron bombs. There's a whole bunch of different types of atomic warfare that you could study or you can get to learn about. But that is not for biological purposes. But just for your own understanding, that amount of energy, when you release all of that stuff that's in the nucleus, all of that energy that is released from the nucleus, that amount of energy that gets released is what causes the neutron or the atomic bomb. Right? So there's a ton of energy focused in the nucleus. The nucleus is designed to keep things together. In the nucleus itself, protons and neutrons are very, very tightly together. And then as the orbits get further and further away, it keeps the majority of the electrons close to the nucleus as well. What happens when the electrons leave? Well, sometimes sometimes good, sometimes bad, but that's what we're talking about with chemical reactions here. So we're only worried about chemical reactions. It's your job. It's hard for me to sort of illustrate what this looks like, but I want you to study on your own the idea of isotopes. And an isotope is when you move, you either add or subtract neutrons from a nucleus, but you do not add or subtract protons or electrons. And I'll give you an example of an isotope. So there are 3 hydrogens examples, and if you modify the number of neutrons in a hydrogen atom, you can either get a hydrogen atom actually, that's wrong. So deuterium has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. And then the left-hand side, the most abundant hydrogen atom is 1 proton. So I'm going to put 1 proton here. Deuterium has 1 proton and 1 neutron, or 1 0. And tritium has 1 proton and 2 zeros.
So isotopes, just so I'm understanding, the same number of protons but different number of neutrons.
Isotopes are meaning the same number of protons but different number of neutrons. And as a result of the different number of neutrons, the mass of the left-hand atom of hydrogen, let me just show you this one, the atomic mass of this is 1, the atomic mass of deuterium is 2, and the atomic mass of tritium is 3. So the atomic mass can either be a lot higher or a lot lower, and there's varying amounts of these elements these isotopes in our body and in the environment. When you then take the average abundance of each of these isotopes, and you take the average mass of them, and calculate the average mass, you then might get, if you look at a periodic table, the mass of hydrogen is not 1.00, the mass of hydrogen is like 1.002 or something like that. So what that means is that there's a small amount of deuterium and tritium in the environment, okay? So you should understand about isotopes a little bit. So let's talk about ions. We're worried about ions here. We're worried about talking about the periodic table. The periodic table that I showed you had 18 columns here, and I'm worried about the first 2 columns, then we're going to skip a bunch, and then we're going to worry about the last 5 columns. So I'm going to talk about columns here, and we're talking about ions. And we're moving electrons. That's all that we're doing here. We're moving, either one thing is losing electrons, another thing is gaining electrons. So now we're going to talk about the columns here. So we're going to do columns 1 and 2. And then we're going to skip a bunch of columns. why the hell I do that. Columns 13, 14, 15, and 16. S- 17. All right, and then we're going to say column 18 is an inert gas. An inert gas or a noble element means that it doesn't react, it doesn't do anything. If you find it in your body, it comes in your body, it leaves your body, it doesn't do anything. So inert gases, column 18, do not react. So let's worry about the first row, and then I'll start drawing the second row. The first row is that hydrogen. Oh, wait a minute, let me change the color. Okay. There's hydrogen, and then at the other column here is helium. Hydrogen has 1 electron. Helium has 2. The first shell here has 2 electrons. The first shell. When you're worried about electrons here, think about electrons as being on a parking garage. If you pull into a parking garage, this morning I pulled in the parking garage, first floor was full. So what did I do? I went to the second floor, that was full, so I went to the third floor. Right? So you basically want to get as close to the bottom as you can, or you want to get close to the stairs or to the elevator. Right? So not all of these parking spaces are created equal. Not all of these places where these shells are created equal. We're not worried about the different particulars of the shells. There's different orbitals and stuff like that. And that's for chemistry. Right? So I'm just worried about the first shell and the second shell, and then really gets into the third shell, and then I don't care anymore. So the first row is hydrogen and helium. The second row is lithium. There's, yes?
Is all this going to be on the slides?
Yes. Now, when I just want to show you where how to draw these things out and how to start studying this stuff. Because the more that you draw this out, the more you're going to retain it, the more you're going to you're going to be able to understand it, and the more you're going to be able to carry it throughout the semester. This stuff that we're talking about today, we're going to talk about it in the end of the semester this year, and then you're going to bring it into AMP2. So one way to study it is to, I sort of get it. The other way to know it is to really, really internalize it and to be able to draw it. If you're able to draw it, you'll be able to remember it more frequently, better and more effectively. Okay? So that's what I'm trying to do. I'm trying to illustrate for you what to draw. And when I get here, this is very, very critical. Okay? All right. So the second row here is, let's see now, there's B, C, N, O, F, and then Ne. Ne is neon. Neon is underneath helium. Now, if you count there, there's 1, 2, 3, 4, 5, 6, 7, 8 elements on the second row here. The first shell has 2 electrons. The second shell has 8 electrons, and 8 plus 2 is 10 electrons. So neon has 10 electrons, 10 protons, and it doesn't really do anything. If we go from there, we're going to start subtracting here. So neon has 10, fluorine has 9. How many does oxygen have?
12.
So
8.
So in red now, this is the number of electrons and protons that an uncharged particle of each of these elements have. Okay? If you look on the right-hand side, fluorine has 9 electrons. Neon has 10. So how many electrons does fluorine need to get to get to 10. Has to get 1 electron. That make sense? How many electrons does oxygen need to get to 10 electrons? 2. Nitrogen, 3. Carbon, 4. Now, look at lithium. What's easier for lithium to do? Gain 9 electrons and go from, or 7 electrons rather, sorry. Go from 3 to 10, or go from 3 to 2.
3 to 2.
3 to 2. So then these two columns here the closer you get to the right-hand side, to these inert gases, the more you're likely gaining electrons. And when I say gaining electrons, give me that. This is mine. She's not getting it. I just gained an electron. Okay? I hope you don't mind. Now, if she and I are going to share this, right? So then she drinks half of it and I drink half of it. No, I'm not letting you have it. Right? So then now we're sharing it. And here, I'll put it down for you. If she lost the electron, she would be in this group. If I gained the electron, I would be in this group. If we were sharing the electrons, we would be in this group. So there's 3 ways of dealing with electrons, or to tracking electrons. Electrons have negative charges. When you gain an electron, what happens to your charge? It goes down, and that's confusing. When you lose an electron, your charge goes up. And so if you look underneath the rest of the periodic table, underneath lithium is sodium. And you notice I put up at the top here of this picture, there's Na+. And underneath fluorine is chlorine, Cl. And I wrote Cl-. So what does Cl do? Cl gains electrons. What does Na do? Na loses electrons. So in what cases now? I just stole Finn's coffee. Right? Finn is now sodium, acting like sodium, and I'm acting like chlorine or fluorine. Okay? So these columns here, 13, 14, 15, 16, 17, and 18, 1 and 2, these columns mean something. Generally, the rows just give you bigger and bigger elements. The columns tell you about reactivity. When we worry about reactivity, these 3 are very, very important. Nitrogen, carbon, oxygen, and hydrogen. Those are the most important ones. Electrons are the most important part of these atoms. So let's talk about the outside of the atoms here. The atomic number, or the atomic amount of carbon, is 6. Okay, so in other words, carbon has 6 protons. Carbon also has 6 electrons. Now, I'm going to draw carbon. I'm going to draw this. So the first shell of carbon is full, so there's 2 little dots there. And then carbon has 2 plus 4 is 6. Okay? So I just accounted for all of the electrons in carbon. Let's do that for nitrogen. If you just look at this now. So there's 6 plus 1 is 7, so we're just going to fill in this initial shell, and then I'm going to put an additional electron in the outer shell, and I'm going to do that for nitrogen and oxygen, and then I won't bother with fluorine. Okay, so carbon. electrons come in pairs, generally. So now, if I were to draw this electron configuration of nitrogen, this would be wrong because there would be, I need one more, right? Nitrogen has 7, I drove 2, 4, 6. So nitrogen is there. And then oxygen is here. Now, I don't care if you know this, right? This is not important. Well, sort of important. What I care about is how many chemical bonds can each of these make? That's what's critical. I said that electrons come in pairs. There's a pair here, pair here, pair here. I also said that these things try to fill out the outer shell. Fill out the outer shell. They want to fill out the outer shell. If you're going to fill out the outer shell, you're going to need more electrons. How many do you need to fill out the outer shell? Here, you need 4, 3, and 2. Okay? How would I draw that here? I'm going to put a red mark here and here. 1, 2, 3 there. 1, 2, 3, 4. So this one will make 4 chemical bonds. This one will make 3, and this one will make 2. So all these elements are trying to do is to fill out their outer shells. So there's 1 chemical bond there, 1 chemical bond there. So the idea of valence is when you're looking at the number of electrons in the outer shell, or conversely, the number of electrons that you need to fill the outer shell, depending on how the question's asked. Okay? So let's ask a hard question. Based on what we've talked about so far, what would hydrogen be? Speak louder? I can't.
Wouldn't hydrogen make like a lot of bonds?
So they will make a lot of bonds. They do, it's a very reactive element. But how many shells does hydrogen have? How many electrons does hydrogen have? How many chemical bonds can hydrogen make? One what? One bond? How many shells? Oh wait, what's my favorite bone? Come on, someone. Tell me, what's my favorite bone? Come on. That one. Right, so hydrogen will make has one shell, right? How many electrons does hydrogen have?
1.
Jelly, right? See that? 1, right? And how many, what, I don't know. Right? So what is hydrogen trying to do? It's trying to fill out its outer shell so that it either has 2 electrons or conversely no electrons. So that's weird. Let's talk about that. So there's going to be 3 ways of talking about hydrogen, right? So hydrogen, when you're in its natural form, that will be that way. There's also something called a diatomic gas, where you have, diatomic means 2 of something, and in this case, we have 2 what? We have 2 hydrogen atoms that are sharing electrons. So in this case now, one hydrogen brings one electron to the equation, the other one brings the other electron to the equation, so they are now forming a chemical bond. They're sharing electrons. It doesn't happen very often. H2 is a very chemically reactive element. And so when it's present, there's things like explosions that happen. So it doesn't, it's not too stable. Most of the time, what you see is this. What does that mean when you see H plus?
Positive.
So positive what? So positive, so the number here, whenever you see a positive or a negative without a number associated with it, that you have to assume that it's 1. So this is positive 1. So that means that this thing right here has lost its electron, has 1 proton, and may or may not have neutrons. That's a different question. So this has lost an electron and has 1 proton, definitely. Okay, so the charge here is positive 1. If I write Cl1 negative, that's the charge is negative 1. Na positive, charge is positive 1, and so on. This thing here is super important, and there's a couple of different ways that you'll hear me talk about it and refer to it. There's, let's see here, you'll hear me call it the hydrogen ion, hydronium, and there's also going to be, what's the third one? I forget what the other one is. I most of the time talk about it as being a hydrogen ion. Most people will talk about, books sometimes talk about it being hydronium. So now I have on the board right there 4 elements with their respective outer shells drawn. And let me just see if I can, all right. That worked.
Could you repeat what the H plus means?
The H plus, that one right there, means that that element, that atom has lost an electron, it has 1 proton, and it may or may not have 1 or 2 neutrons. I will not ask you about how many neutrons it has. Okay? I would ask you, if you see a H plus, what can you tell about it? Definitely has a proton, it's definitely lost its electron. So we're worried about 4 elements here. So we're worried about 4 elements, and those 4 elements are hydrogen, oxygen, nitrogen, and carbon. Whenever you have hydrogen, nitrogen, oxygen, and carbon, they want to make these, how many chemical bonds they want to make? 1, 2, 3, 4. Why did I write HOCNC? Because 1, 2, 3, 4. It's easy to remember. Okay. If you had chemistry with Mr. Orton, this should all be review. Now, what might be different is when we start drawing these macromolecules. We're going to transition into making macromolecules. The word macro means big. Big molecules, these typically are biologically important molecules, and they come in 4 varieties. These varieties right here. Before we get to these varieties here, does anyone have any questions about what we've done? And by the way, I'm also going to try to figure out how to save this as a PDF and then post it onto Brightspace. Okay. And it might, I'm not sure how it will look. And this is literally the first time I've ever used an iPad lecture.
Really?
Yeah. So I practiced it last week and over the break and stuff. But so I haven't used this. So any questions now?
So everything is on the slides.
Yes. Yes. If I can draw it though, you should draw it. Just as a rule of thumb. The best way to remember this stuff, by the way, how many notes am I using right now? How many book notes do I have in front of me? No, none, right? Do I remember this off the top of my head?
Yeah.
That's what you want to do. Now, are you going to know it as well as I do? I'm a little old, right? Maybe not. But you want to know more than what you do before you came in today. By the way, the reason why I'm doing this is that I literally have diagrams here where if I was started here on this board, started right over here, I went all the way across, I might finish over in that corner over there. A single diagram. So I want to try to make it so that hopefully it's reproducible, and hopefully it's easy accessible. I'm not. So I'm trying to adapt my teaching styles here. So I'm trying to learn while you guys are learning. So let's start making macromolecules. But before we make macromolecules, let's start talking about chemical formulas, chemical structure, and how to draw things. Okay? So first things first. What is that molecule? H2O, okay? What's another name for that?
Water.
Water. Actually, let me do this. Now, I am going to draw another atom, molecule of water. And then I'm going to put little blue dots there. The reason why I'm putting those little blue dots is those little blue dots have different small charge on them. So we have two water molecules, and water molecules are sticky. They're not super sticky, but they're reasonably sticky. And the reason why they're sticky is the difference between this thing and this thing, oxygen and hydrogen. Oxygen likes to steal electrons. Hydrogen likes to give up electrons. Sometimes oxygen will steal the electron away from the hydrogen. You saw me stealing Finn's coffee. If Finn and I were sharing it equally, then there would be equal sharing of it, right? But if I drink 3/4 of it and she drinks 1/4 of it, then I would have a little bit more of it, or a little bit more of it than her. The positive means less, fewer electrons. That negative means more what? More electrons. So oxygen always has a slight positive. And now what does that D mean? That D is a delta, and that delta is Greek for a change or a difference. It's basically it's the only time you're going to see this terminology here. So this means there's a slight negative charge here and there's a slight positive charge here. And this means there's a slight negative charge here, positive and positive, positive. And what I said at the start when I started talking about water is that I said water is a little sticky. Hopefully all of you did this morning. Hopefully, and I don't want to find out if you haven't. Hopefully you all showered this morning. Right? When you get out of the shower, water, you're not dry, right? I don't think. I personally wasn't dry this morning when I was out of the shower. It was sticking to my body, right? Why is that water sticking to my body? These charges here. So water sticks to my body. In addition, the water was in droplets, right? And because the water were in droplets, they were sticking to each other. So they stick to each other, they stick to other things. When they stick to each other, that's called cohesion. When they stick to other things, that's called adhesion. And water molecules are very, very critical in the function of life, the presence of life. They're so critical that if you take astronomy classes in the future, what you'll spend a lot of time figuring out is where is water present in the cosmos? Where is water present? Because if water is present, there's a reasonable chance, there is a chance, a better chance of life being present there. If water is absent, then it's virtually, as far as we can know, it's virtually impossible. So this is how critical water is. Once again, water, how did I know that water is H2O in addition to the formula, right? Where did I put? Oh, so right here, water has, oxygen has 2 chemical bonds and hydrogen has 1 chemical bond. So this rule right here that I just boxed in blue, you have to remember that. And this shows you 2 examples of 2 water molecules. The formula both is H2O. So there's 2 hydrogen and 1 oxygen. So now, given that we have these rules in the upper left-hand corner, I'm going to draw some more combinations here. And I want you guys to tell me what we're looking at. Whoopsie, what was that? We're not worried necessarily about naming the compounds, but we are worried about whether these compounds are accurate, whether they should have charges on them, what the chemical formula will be, and then the next drawing will be different views of this, ways that chemists then start making chemical shorthand. So first of all, look at this one on the left-hand side. So question number 1, does this formula, does this configuration adhere to these rules? In other words, does the carbon have 4 chemical bonds and each oxygen have 2? No? What do these lines mean? What does that squiggly, that line and that line, that is meant to be a straight line. That straight line, that straight line. Give myself a break here. So 1, 2, 3, 4. How many chemical bonds can carbon make? 4. Okay, so that's made 4 bonds. How many chemical bonds can oxygen make? 2. 1, 2, 2, 1, 2. So that's correct. What's the chemical formula for this? CO2. Is this present anywhere in this room?
Yeah.
Where? Everywhere. In your body, in my body, in the atmosphere. That's called carbon dioxide. What's the chemical formula of this? What is it? CH4. It's called methane. Chemical formula of that.
Oh. Wait, so that's a squiggly line?
Which one? That is meant to be a straight line.
Okay, so
All these lines are meant to be straight.
It's not an equal sign, but it's.
So this equal sign, and that equal sign meant to be 2 parallel lines.
Okay.
And all of these lines mean what? It means that the elements are sharing electrons.
Okay.
Okay, so now we're sharing the water bottle, right? If we never let go, right, for the rest of our lives, right, then we're never gonna, right, we're always gonna be sharing this water bottle. If this water bottle was an electron, then we're sharing that electron. Now, if we have 2 water bottles, then we're sharing 2 electrons. I don't want to drop it because it'll break the table. The thing's so damn big. My daughter has these enormous ones. It's like, why are they so big? All right, so that means 2 sharing of 2 electrons. That means sharing 1 electron. That's sharing 1 electron.
Okay.
One pair of electrons, right? This bringing 1 to the table, and that's bringing 1 to the table. Okay?
So, if you're sharing 2 water bottles, would be 2 chemical bonds?
Yes.
So the lines indicate how many bonds they're sharing.
So the lines indicate how many bonds they're sharing. Correct. How many electrons they're sharing. And there's one from the right and one from the left. So, whoopsie.
Wait, so is a chemical bond the same thing as an ion bond?
So, hold on a second.
Sorry.
Is a chemical bond the same thing as an ionic bond? An ionic bond is a form of a chemical bond, and I haven't talked about different types of chemical bonds yet, but I will.
How do you figure out which letter comes first?
So don't worry about which letter comes first. I'm not as worried about that. Generally, carbon comes first, followed by hydrogen, and then other things. But there's a whole sort of set of rules about that, but that's not something that's terribly important here.
Okay, just to make sure, that box you made is like the limit.
This box,
Yeah. That's like the limited amount for each element?
that's the number of chemical bonds for each of these 4 elements.
Oh,
Okay? So if you're drawing a carbon, look at this carbon right here. How many chemical bonds should it make? 4. There's 2 right there. 1, 2, 3, 4. Okay?
So then what about the other? Oh, that's connected to the.
This one right here. All right? 1, 2, 3, 4. Okay?
I'm explaining cohesion and adhesion.
Now, there's also chemical shorthand. Lots and lots and lots and lots and lots of chemical shorthand. And that's what we're going to next. All right, now, first things first, we can have macromolecules, we can have very, very big molecules in our body. And let's start drawing one simple one.
I don't know if those are.
What's that?
I said that doesn't look so simple.
That doesn't look too, what?
Simple.
Simple? This is very simple. All right, now.
Wait.
All right, so I've drawn 4 parts, or perhaps, depending on my drawing here, on the left-hand side, we have carbon. Am I done with this drawing? Why not? Because I have 4 chemical bonds and I've only counted for 2 each of these, so I'm not done here. Then I have this one with dots, this circles, and this one with circles, and then there's 2 double bonds, and then I have this circle in here. What the hell does that mean? We'll get to that in a second. Here. Right? I'm not done here, so let me go into that. I said that chemists have lots of shorthand. One of the most abundant elements in the world is hydrogen. Hydrogen is everywhere. So as a rule of thumb, if you're going to assume something, assume, and there's no other information, then you assume that there's hydrogen. If I show you this molecule on the left-hand side, what's the chemical formula of that? Let's just start with carbons here. So there's 1, 2, 3, 4, 5, 6 carbons. Yeah.
So wouldn't it be 6CH2?
Well, wait a minute here. So the chemical formula, oopsie. So the chemical formula of this will be C6 and then H. Then we got to figure out how many H's. How many H's? 12. For each one, there's 2. So C6, H, 12.
So, if something's like missing bonds, we should assume that there's hydrogen there.
So if something is missing bonds, then you should assume what hydrogen's there. Now, what's the next one then? If this is correct, I'll give you one bit of information about this. If this second molecule is correct, and it is, what's the chemical formula? What haven't I told you?
What?
Whenever you see a circle there or an intersection that is not illustrated, right, or that's not indicated, you could assume that's carbon. So that right there is carbon. So the 2 elements in this compound are carbon and hydrogen. How many carbon do we have?
6.
How many hydrogen do we have? I didn't draw them out because we just assume that they're there. Now, look at that molecule and then the next one. What's the difference between the second and third molecules? There's what? There's 3 lines right here. So there's a double bond here. Whoops. There's a double bond there, and a double bond there, and a double bond there. All right? So let's start with basics here. What are the elements involved?
Carbon.
Carbon and hydrogen. Now, how many carbon are right here? There's 6 carbon. So I've drawn this 4 times, the same shape. And how many hydrogen? So there's, if you look at, let me see here. So this carbon right, wait a minute. This carbon right here at the top has one, can you guys see the red dots that I'm putting? 1, 2, 3 chemical bonds. So this carbon has 1 hydrogen. This carbon, the next carbon to the right, has 1, 2, 3 chemical bonds. So there's 1 hydrogen. The next one has 1, 2, 3 chemical bonds. Hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen, and 1 hydrogen. So what's the chemical formula of this? C6H6. And finally, remember I was saying chemical shorthand. I don't feel like drawing the individual double bonds, so I'll just draw a circle. The last molecule here is what's called a hexagon, I mean. So there's 6 carbons, and they have 3 rotating chemical bonds, double bonds here. So the formula here is C6H6 as well. Okay?
How do you know what type of chemical we're working with if we don't have the H?
How do you know that? You have to remember the rules. I'm going to show you different views of these pictures, right, in lecture notes. And the question will be, what's the chemical formula? Which elements are there? What's the charge on this element? What's the charge on that element? By the way, charges here. How many negatives and positives do you see here? None. So what are the charges?
Neutral.
0, right, or neutral. Right? So there's 4 elements, or 4 compounds right here. They have, 2 have 1, 2 have another formula, right? And by the way, back up. all of this is for you to study if you were down on the main campus. They would not bother doing this for you, okay? At the top here, we talk about C2H4, CH4, CO2, and H2O. All of those things, we talk about different sharing of electrons. And none of this is what I want to talk about. Okay? What do I want to talk about? The
Macromolecules.
only thing I want to talk about is making of these things. Right? And there's a last thing that we're gonna sort of, let me bring you back to.
Dr. Lindsay, I just have a question.
Yep.
So are we assuming that each carbon has 2 hydrogens attached to it?
Unless, if you're assuming on the right-hand side, you're assuming wrong.
On the left.
On the left-hand, so, on the far left-hand side, I'm gonna draw it in blue. In this case, yes, because you can see that there's hydrogens there, right? On this one right here, you can assume that as well, the second one.
And why would we assume that for the second one?
This, because hydrogen is everywhere, and that's one of the chemical shorthands that you're gonna just assume.
Okay.
All right, now, there's one last thing that I want to talk about in terms of the carbon, nitrogen, oxygen, and phosphorus, and that's something called functional groups. So there's about, I think the book talked about 6 or 7 different types of functional groups. I'm going to talk about 3 in particular. And in particular because I want to start talking about proteins. The first functional group is called an alcohol or alcohol. And basically you're going to see it go in OH. So a carbon with an OH in it. The second one is going to be an amine, and you're going to see it with a carbon, and then an NH2. And then the last one is called a carboxyl group or a carboxylic acid. And generally what you see it written out as COOH. Now, remember the rules of bonding. Right? The rules of bonding state that oxygen has to have 2, hydrogen 1, nitrogen 3, and carbon 4. In this case, there's a COH. So this carbon's got to be bonded to something. We don't know what the hell it's bonded to, but we'll worry about that later. Same thing's true here. This nitrogen is bonded to something. This nitrogen bonding, the rules for nitrogen are 3, right? Bonding rules for hydrogen are 1. Bonding rules for oxygen are 2, right? So this is accurate, and this is accurate. But look at how I wrote this. So this one I wrote OH, NH2, N12, right? Now, COOH. You will see this written like that, and that does not mean that the 2 oxygens are bonded to one another. Right? So that does not mean that. Because when you're looking at this COOH group or a carboxyl group, that is what you mean. Now look at this. this oxygen has 2 chemical bonds. This oxygen has 2 chemical bonds. This carbon, 1, 2, 3, 4 chemical bonds. So it obeys the rules of bonding patterns, but it's just written slightly. Why is it written like that? I'm not sure. But this means this means that, and that means that. Okay? What's it?
Did you redo the pointing for the third one?
What'd you say?
Did you redo the pointing for the third one? For, how much the oxygen and carbon was given? Carbon's 3 and 2. I just wanted to see the points.
The points? So carbon has 1, 2, 3, 4 chemical bonds.
And then the oxygen.
1, 2. This carbon is bonded to this oxygen is bonded here. Now, so this oxygen has 2. If you look at this part right here, and then you look up here, this part right here, they're the same. Right? So that when you have an alcohol group with a double bonded oxygen, which is called another thing called an aldehyde, but I'm going to skip that for right now. That, when you combine those, is called a carboxyl group. And this carboxyl group is really, really important. It's really important. You'll see it written like that, but that's not what you mean. What you mean is this. Okay? So, first thing we're going to start drawing is a protein. Then we're going to start talking about the chemical reactions of proteins, the structure of proteins, how you make proteins. We're going to get a lot of that. Okay? Does anybody know what the functional group or what the monomer of a protein is?
Isn't it
An
gonna be,
amino acid.
A and T?
No. Thank you for trying. No, so there's an amino acid, right? I've already showed you the name amino acid. I've shown you what an amine group looks like, and I said carboxyl group. Well, that name carboxyl also will be called carboxylic acid. So what I've just told you then, I've just shown you the structure of an amino acid. Okay, so here's what I'm going to draw it, and I always draw it the same way. And once again, how many times have I done this? I've done this a lot. How many notes do I have up here? Literally, the only notes that I have is the second row of the periodic table, because I don't bother remembering that, and the first row. Right, that's literally all that I have. I mean, the rest of it is just, actually, the rest of it is people's names in lab, right? I'm trying to remember. So this is important. What I'm going to draw is a central carbon, and then there's going to be, on the right of it is going to be an acid, and on the left of it's going to be amine. Okay, and that central carbon will be one color. Let's see here, let's do that. Yeah, that central carbon will be blue. The amine group, let's see. The amine group will be black. And then the acid group will be red. All right, so this is called an amino acid. This is analogous to me drawing a picture of Jaharlan, but this is my picture of Jaharlan. You ready? All right, so there's her hair. So you know it's not me, but is this accurate? Not really, but that's at the level of detail, right? when you see this R right here, there's a whole bunch of complexity here, and I don't care if you know that complexity. What I'm gonna do now is I'm gonna copy this amino acid, and I'm gonna put a little plus sign right here. We're gonna put it right over here, but I'm gonna change this R to an H. So this amino acid is called a generic amino acid. That's a generic person, right? We don't know who it is really. Right? This is a generic amino acid. Okay, I'm gonna just do this in black now. Besides the color, what's the difference between this? The difference between this is that hydrogen right there. There are 20 amino acids in our body. There's actually more than that, but there are 20 major amino acids. The one amino acid that I'll ask you to recognize is glycine. Glycine has what's called the R group. This R group right here can be very, very big. It can have positive, it can have negative charges. It does a lot of things. One of the things that it does, if any of you have long curly hair, I'm jealous. But if you have long curly hair, that means the amino acids in your hair is different than someone with long straight hair. In either case, I'm jealous. Why is that? Because I have a lot. So if you have curly hair, it means you have a lot of cysteine or sulfur in it. If you have straight hair, that means you don't have a lot of that amino acid. Glycine is one example of an amino acid. There's another 19. This is just a generic amino acid. So the first thing we're going to do is we're going to say, how do we combine these two? When you're combining two monomers here, this is a monomer of a protein, this is an amino acid, and this is an amino acid, and that term monomer means one. Yes?
Okay, so now I get why DNA is also macro.
Yes. And since you brought that up, so the DNA, RNA, ATP, and ADP, and then there's others too, but those are the only ones we're going to worry about in this class. Now, when you, so we're going to talk about monomer. Oopsie, monomer. When you take two monomers, 1 + 1 is 2. When you add one monomer to another monomer, you get what's called a dimer. The dimer here, in this case, is called a dipeptide. Whenever you see the word peptide, you should remember, you should think of proteins. And a peptide and proteins go together, right? There's something called a polypeptide. Poly means several, di means 2, tri means 3. 3 what? 3 amino acids, 2 amino acids, several amino acids. A protein might have thousands or hundreds of thousands of amino acids. So we're not going to get that detailed. But what we are going to do is we're going to say, how do you join two monomers? And the very simple thing here.
Oh, so are both amino acids together one monomer?
So no, so on the left-hand side of this is one monomer. So this is one monomer right here. This is another monomer right here. And what we're going to do is we're going to make a dipeptide or a dimer. Okay? And when you're making this, when you do this, what you do is you look for 2 H's and an O. And what do you get when you make 2 H's and an O? What? You make water. If you lose water, what happens to your body? You get dehydrated. So you're losing water, and that is called this whole chemical chemical reaction is called a dehydration synthesis. When you synthesize something, you're making it bigger, and then we can also do it the opposite way too. And we'll talk about that in a minute. But let's continue on with this. So what I'm going to do is I'm going to draw that first amino acid, that generic amino acid, and then I'm going to draw the glycine molecule, and I'm going to put a red line between them, and that red line is going to start at that nitrogen, because if you look at this, now I have this nitrogen that has that chemical bond broken, and I have this carbon with this chemical bond broken. So guess what? This carbon is going to then get joined with this nitrogen, and that new chemical bond will have a name, and I'll talk about what that is in a second. So here's what I'm going to do. I'm going to draw this part right here, and then I'm going to draw this part right here, and then I'm going to try, hopefully I'll remember to do this, put a red line between that N and that C. In both cases, I'm drawing an amino acid here. I know that there's an amine group and there's an acid group. There's an amine group and an acid group, so that I'm just drawing it the same way. And the one thing I need to remember here is I need to remember to keep out these two hydrogens and an oxygen. Okay, so I'm going to start that, and I'm going to try and draw it right there. So I'm copying this, hopefully accurately. Okay. So I think this generic amino acid is accurate. It's right here. The one thing that's missing is that OH. And then this glycine, with one thing that's missing is that hydrogen. All right? It doesn't matter which hydrogen you take. If you want to take that one or that one, it doesn't matter. They're the same. You have to take that OH because that's the only one available. In either case, you want to get rid of water, and so you're going to dehydrate the molecule, you're going to lose water. That is called a dipeptide. There's two amino acids. And then if you then string these along, do hundreds and hundreds or thousands and thousands of times, then you'll build up ultimately to what? To a protein. When you have two amino acids joined together, there's this right here is called the peptide bond. All of these other black lines, none of them are peptide bonds. The only peptide bond you have there is that red line. Okay? So peptide bonds occur between the amine group and the acid group of adjacent amino acids.
So a dipeptide is two amino acids together?
Yes. And then a polypeptide is if I put one or two or three more, that would be a polypeptide. And then if we get hundreds or thousands more, then we get a protein. Depending on the structure of the protein. There's two important proteins in this class. Two proteins here.
So all of like the diagrams that we've done previously, those are all amino acids, not proteins.
Say that again?
So all of the diagrams that we've done so far, like the H, that's all an amino acid.
So this is an amino acid and that's an amino acid. This is a dimer or a dipeptide.
Okay.
Okay? There's two proteins that I'm gonna talk about in lecture here. One is hemoglobin, the other is collagen, very, very different shapes. This one looks like a snake, this one looks like an elephant. I mean, think about it in those terms, right? Long and skinny, basically a big blob. But regardless of what you're talking about here, this big blob hemoglobin, long and skinny, this snake-like, your body assembles it in the same way. It does this. It does dehydration synthesis to make things, and it assembles it, these peptide bonds, that make these new peptide bonds. And how does the molecule change? The way the molecule changes is this thing right here. If you have a whole bunch of glycines with these little H's right here, then you have one molecule. If you have other things, you have another molecule. Case in point, look around you, you have long straight hair, you have one set of amino acids particularly in the collagen and in your hair. Right? If you're curly hair, you have a different set. So the structure there differs. Okay? And as a result, the function might differ. Okay.
So why was there a circle on the
Right here?
R?
I don't know.
What,
So it's always been that way. It's just because.
what
and
is the R for? What is
the R means that this is called a generic. Whenever you see an R, first of all, is not a chemical element.
Okay, so it's just being
Right?
generic amino acid.
It's a generic amino acid, right? But I don't know the answer to your why is there an R, right, circle? But it means generic amino acid. All right. One last question here. What is the chemical formula of glycine? So first things first, let's start, just tell me what the elements are.
C.
Carbon,
Carbon.
nitrogen, oxygen, and hydrogen, right? So let's do CnOH. So what's the chemical formula? And I will ask you this too. So CnOH. How many carbons are in this molecule? How many nitrogens? What do I do when I have just one in this? I don't put anything, right? I just assume that how many oxygens? And how many hydrogens? 1, 2, 3, 4, 5. So the chemical formula of glycine is C2NO2H5. You might see them, it might be CH5, C2H5, and O2. It's written differently. I would not ask you what the chemical formula of a generic amino acid is because that's not complete. Okay? So, we've just talked about proteins. Now we're going to start using our tools even more dramatically. We're not going to get done with this, unfortunately. Whoops. Why is this moving? I don't know why this is moving on me. So, the formula for carbohydrates, yeah, maybe I'll move over here. So for carbohydrates, we're going to start with a monomer. Just like for proteins, we started with the monomer. The monomer of a protein is an amino acid. The monomer of a carbohydrate is a monosaccharide. The monosaccharide, that mono is one. Saccharide is sugar, that suffix saccharide, C-C-H-A-R-I-D-E. That saccharide means sugar. So typically carbohydrates are associated with sugars. And the simplest carbohydrates are sugars. So first things first, we're gonna do C6H12O6. Now, I'm gonna I draw it the same way every year. And so it's easy for me to remember.
Wait, why is it called a monosaccharide?
Why is it called a monosaccharide? The answer, I'm not sure. But the Greek or Latin for saccharide is sugar.
Sugar?
Why? Yes. So why is it mono? Because there's one, and when you string them together, then you make a polysaccharide or a carbohydrate. Okay? Now, once again, these black circles, what element does those black circles represent? It's carbon. Okay, how many carbons do I have in this picture? 5. Am I done with carbons? No. All right, now. Okay, what do those vertical lines mean? It means there's chemical bonds that are going up or down from that individual carbon. So now on the right-hand side, there's a carbon with that central, this carbon right here, right, has 4 chemical bonds. Right? And what I'm doing right here is I'm filling in, let's see. Wherever there's a carbon, there has to be 4 chemical bonds. And then what are we doing here? We're putting 6 oxygen and 12 hydrogen. So C6H12O6, let's count for, the carbons are easy, right? Because there's 5 circles and there's 1 carbon. So let's count oxygens here. So there's 1, 2, 3, 4, 5, 6. So C6H, I'm not sure about that yet, but O6 is correct. Let's talk about hydrogens here. So at the top right here, there's 2 plus 1 is 3 hydrogens. Then there's 4, 5, 6, 7, 8, 9, 10, 11, 12. So what's the chemical formula of this? Okay, so that is a monomer of a carbohydrate. Now, if I knew how to use this iPad better, I would copy it and paste it twice and make it easier on me, but I can't do that yet. I tried to and it screwed it all up. So what I'm gonna do is I'm not gonna label this anymore. I'm not gonna count anymore. I'm gonna draw 2 more monosaccharides. I'm gonna leave this one over on the left. I'm gonna draw 2 monosaccharides and I'm gonna show you dehydration synthesis for 2 monosaccharides. And guess what we're gonna make? We're not gonna make a monosaccharide. We're gonna combine 2 monosaccharides. We're gonna make a disaccharide, okay? So, all of the monosaccharides are gonna have the same, both monosaccharides are gonna have the same formula. Depending on how you configure it, the formulas will change. You can make glucose, galactose, and other monosaccharides, and I'm not gonna ask you, I'm only gonna worry about one thing, and this is glucose. What I've just drawn for us is pretty close to being glucose. It may be, so anyway, now, one of the things about this, now we're away from chemistry. We're into the biological basis of chemistry, or biochemistry. I'm not gonna fill it in all the way, because what do we worry about here? We're worried about oxygen and hydrogens. The hydrogens, if I didn't bother filling them in, you know that the hydrogens are there. I'm going to fill in, I'm gonna label OH here in red, and that H right there. So on the right-hand side, I've just added all the oxygens. 1, 2, 3, 4, 5, 6. On the left-hand side, I'm gonna add the oxygens in all but one case. Now, you see this? You see this? We are not reading here. This is not ho, ho, ho. And this is not O. Right? We're not reading English here. This is chemistry. So this means that this oxygen is bonded to that carbon and that hydrogen. This means that oxygen is bonded to that carbon and that hydrogen. Okay? So I don't care if it's OH or HO. I only care that the oxygen is bonded to the carbon and the oxygen is bonded to the hydrogen. Okay? So that's the first thing. Why are these red? We're going to dehydrate the molecule. And if you dehydrate the molecule, you lose water. Just like we lost water in the previous example.
Where's the sixth carbon?
For which?
For the second.
This one?
The second.
This one? So there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
Oh, you're counting the top one?
Yeah, so each of these circles right here are carbon. The oxygens are indicated. Okay? Now, what is here or here or here? There's hydrogens. I didn't bother putting them in. Right? I will put them in. If you see that, right, on a diagram, you should just assume there's hydrogens. But you should be able to assume they're hydrogens, and therefore you should add them into the chemical formula. Okay? Now I'm going to draw a disaccharide, and I'm not sure if this is going to be able to let me go. I might have to move down. Actually, I think I'll just move down to make it safe and try to finish this up. So what I'm going to do is I'm going to move this up. I'm going to draw this molecule and this molecule. I'm going to join them together at this chemical bond. I'm going to draw a red line between that carbon and that carbon. No, I did that wrong. Let me back up. Let me see. I'm sorry about that. I'm so focused on how I'm drawing it, I'm not worried about what I'm drawing. So I messed up right here. Okay, so I'm going to draw this again. we're going to draw a disaccharide. There's two saccharides joined together by this thing right here. This is called dehydration synthesis. And once again, I'm going to do it down here. Okay? All right, so let me just finish up here, and I know what time it is, and I'm taking longer to do this because of this technology. So, what do I have here? I have C6H12O6, but wait a minute here, I didn't finish it? Yeah, I didn't finish it, so you have to finish it. I will get to it when I'm after class. I'll finish this, I'll finish this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, it's almost done. What's important? If you look up top there, I have an H on the right-hand molecule and an OH on the left-hand molecule, and I lost that. That water is gone. Now, what's remaining? That remaining one is that O up there. That remaining O is right here. When there's an oxygen that joins one monosaccharide to another monosaccharide, that oxygen, that chemical bond is called a glycosidic linkage. The only place that you find glycosidic linkages in macromolecules is in carbohydrates. So a carbohydrate has monosaccharides. They join together through dehydration synthesis. Those monosaccharides have the same chemical formula. They're C6H12O6, generally. They're the only ones that I'm going to worry about. When we talk about the chemical formulas, that will be the one that I will definitely ask you to remember. But the other thing is that there are other monosaccharides. And I might ask you to, what's the chemical formula of that? What are you going to do? You're going to use the same rules that we've just gone over, and you can calculate that as well. Okay, and you would carbon, hydrogen, and oxygen. Generally speaking, carbohydrates have just carbon, hydrogen, and an oxygen. Proteins have carbon, hydrogen, oxygen, and nitrogen. Some proteins have sulfur in them, not very many. Lipids have carbon, hydrogen, and oxygen. Until we add the fourth element, and that's phosphorus, and then we'll talk about that. So far, just review where we started from this. Yeah.
You dehydrate the carbohydrates to combine them, right?
Whenever you dehydrate monomers, you combine them. So in this case, you combined 2 amino acids, you dehydrated them, you joined them. Now we just combined 2 carbohydrates, we dehydrated it and joined them. Guess what I'm going to do tomorrow? We're going to combine parts of 2 things that they're not the same thing, but parts of lipids, and we're going to join them together, we're going to dehydrate it. So if you look at this part right here, we talked about cations and anions, we talked about the basics of the periodic table, then we talked about bonding patterns of carbon, hydrogen, oxygen, and nitrogen. We talked about the different chemical representations of that, right? We talked about what's called cohesion and adhesion with water molecules. Water is very critical here. The different, identifying different chemical formulas. And then we jumped into drawing macromolecules. Tomorrow, we're gonna draw a macromolecule of a lipid, and then we'll summarize it, and I'll talk a little bit about nucleic acids, and then we'll jump right into the lecture on chemistry. Question?
So for like the last thing you did, the CH2OH, is that supposed to be a 2? Or it's supposed to be 12?
Wait a minute. Are you talking about right here?
Yeah.
That is supposed to be a 2,
Okay.
because carbon has 4 chemical bonds. That carbon bonds to that carbon, so that's 1 chemical bond. That carbon bonds to that oxygen, that's 2 chemical bonds, and so there's 2 more left, there's 2 hydrogens. Okay, so CH2OH does not mean that hydrogen and oxygen are bonded. There's 3, right? Here's what this means, since you asked. And okay, that's CH2OH. So that and that are the same thing. Okay? Once again, how do I know that? Right? If you read it literally, that means that oxygen has 3 bonded with 3 hydrogens, and then what the hell's carbon doing? Well, right, so it doesn't make sense. So now why is it written like that? Because. Who wrote it? It wasn't me. I didn't start it, right? But I'm just gonna perpetuate this. Because other biochemists a long, long time ago did it. A bunch of old dead white guys that were much, much older than me started this. And so this is the way it goes. And when you guys get to biochemistry, that's the way you'll do it. And then when you teach this class, that's what you'll do. Because it's standard practice now. All right, so it's a little bit after 11, I think. I think we've gone through a lot of material. So what should you do tonight? Number one, if you cannot write an amino acid or a carbohydrate by tomorrow morning, let me just borrow something. With this much information in front of you, okay? If you can't draw this with this much information in front of you, in other words, nothing, right? If you can't draw that, you're way behind.
You said amino acid in the carb?
What I just did, yes. Right? If you can't do dehydration synthesis, you're way behind. Right? There's a lot of stuff that we're going to be talking about, and I'm going to get even in more detail after we're done drawing tomorrow. So tomorrow morning at 8:30, I'm going to start drawing, and then we'll get into something, and then we'll have a little break, and then we'll do a lecture. Okay? And then we'll figure out what we're doing for Wednesday.
The carbohydrate